So this is the so Dr. Professor Surya Prakash has just mentioned about the devastating earthquakes in India in the last decade. So here we can see that India is mainly divided into this intercontinental region, intraplate region, and subduction zone, and the main collision zone. This is the Himalayan collision zone, which is the most seismically active belt in the world. It is one of the most seismically active belt in the world, and its length is 2,200 kilometers. Is always now and then in every decade we can see that an earthquake were happening, and it is being felt in the Indo-Gangetic plains and up to Delhi, because this Indo-Gangetic place is the seat for the major industrial and the population is there. So any earthquake in the Himalayan is certainly affect the country. So so here, so the most you can see the seismicity pattern the right hand side. So you can see the how the earthquake pattern is. So in the stable continents in peninsular India, there is a only small, very not major earthquakes. This is one of the major one is the 1993 this 30th September Latur earthquake, and the 21st May 5.8 this Jabalpur earthquake, and also we can see that this is a Bhuj earthquake in 2001 in the January 26th. So this is the major seismicity map of India and how the earthquakes were taking place in the country. So what is the earthquake early prediction? Earthquake early prediction is not an earthquake prediction. So we cannot tell that this is when it is going. So when it is going to happen, where it is going to happen, what is the size of the earthquake, this thing, and also earthquake early warning system is not an earthquake forecasting. Just unlike weather forecasting, we can see that next 5 days what would be the other pattern. We can get some idea from the India Meteorological Department and other sources. But it is not like that. It will not tell about what is the timing when the though there are recurrence models are there, but they are all statistical model, but they do not exactly give the information when the earthquake is going to happen, what is the size of the future earthquakes. So they're all just probability context, they give some idea. So but the earthquake early warning is the after the soon after the earthquake, what it does, it may not be possible to predict or forecast the next and when where damaging earthquakes might occur. It is possible to estimate the effect of strong ground motion shaking on surrounding areas while an earthquake is still rupturing. So we can see that here rupture is propagating. So the earthquake is taking place, but the ground motion is happening. But during that time, we can inform to the certain the important nodal areas and nodal places, and this thing. See, there is a strong ground motion is going to arrive. So take care. So this is the earthquake early warning system. This is the principle of the earthquake early warning system, and the lead time and the warning times are very less because the earthquake has already happened, and we are going to inform about the expected strong ground motion in different parts of the areas away from the earthquake. So this is the principle of the earthquake early warning system. So we all know that when earthquake rupture takes place, or so when earthquake takes place, then seismic waves will be generated. This is a natural phenomenon. This is seismic waves will be generated. So the seismic waves mainly, we know that it is a very simply, it is very simple manner. If you have to tell, means there are two kinds of body waves and surface waves. In body waves is the major ones. This is the P waves and the body waves are again P waves and S waves. And there is after the S waves, again the surface waves will come, and they are travel with a velocity of 2.2 to 2.5 kilometers per second, but they are very intense and the periods are very large, and they carry a lot of energy. So but the initial part of the wave, P waves, that is called the primary wave, which travels with 6 kilometers per second, and they are very high energy, high frequency content of about 1 to more than 1 hertz, like that. So in seismology, it is not like electromagnetic spectrum. This is everything. The measurements are confined to the more or less than the 200 hertz only. So the P waves, which are the typically the 1 hertz to 10 to 15 hertz like that, and they travel with the velocity of 6 kilometers per second. They travel with the velocity 6 kilometers per second, and they, because their amplitudes are very small, but they travel faster, and so they will not cause much damage. This thing. So this P waves, initial P waves, can be taken for the taken for the processing to estimate the ground motion at different parts of the areas. So next is the slow and I told you that this is there are two waves, P waves and S waves, and this is the damaging waves are the S waves and the surface waves. They are travel with the velocity of 3.5 kilometers per second. They are very damaging waves, which cause extensive ground motion in the area when they pass through that area. So so you know that the technology has developed too much, is reached to that level now. So we can detect the when the sensors are there very close to the rupture zone, when it is close to the rupture zone, and we can detect that P waves. When we detect the P waves, and then the alert can be passed with the speed of light, that is 3 lakh kilometer per second, and inform to the the important areas, the nodal areas, and for the rescue operations. See that strong ground motion is going to come and take care of that thing. So earlier, this AEW alert provides only a limited amount of warning time, because I already told that because the earthquake has already happened. So after the occurrence of the earthquakes, we are detecting that P waves, and based upon the P waves, we are issuing the warning that a strong ground motion is going to arrive at your place. So this is the major, this is the working principle of the earthquake early warning system. So what is the magnitude? Generally, the magnitude of the earthquake, we know that it is so it's proportional to the amount of energy released at the source. So how the magnitude of the earthquake depends? The magnitude of the earthquake depends upon the fault geometry. So how much volume of the area is involved in the rupturing? So it is the length of the fault and the width of the fault. How much slip has taken between the two sides of the fault? So how much they have moved it? So the complete volume will represent the magnitude of the earthquakes. So the rupture also will not it is not a point source. It takes some time to reach to stop the rupture. So when the rupture has been initiated, we do not know whether it is going to be 5 magnitude earthquake, or the rupture will continue to another may stop or may continue to another 8 magnitude earthquake. So the initial rupture onset are not the true representation of the final rupture sites, final magnitude of the earthquake. That's why in the earthquake monitoring also, so for big earthquakes or for tsunami genetic earthquakes, maybe for large magnitude earthquakes, we generally our magnitude estimations goes wrong, because we do from the initial part of the waves, and there the rupture is still going on, and still going on. So the estimation may come erroneous, and later on we revise the magnitudes to the correct values. So here we can see the approximate estimates of distances and times for the earthquake early warning system. So see, the magnitude is depend upon the how much fault length, fault geometry is involved in the earthquake. So for example, magnitude 5 earthquake is of the fault length 1 kilometer, and it produced in the epicentral area with intensity modified Mercalli intensity scale. So here it is, there are two things are there. One is the magnitude of the earthquake, another one is the intensity of the earthquake. Magnitude of the earthquake will tell about the energy released at the source, that is how much. It depends upon the fault geometry. Just I have shown here how much fault is involved, how much rupture has taken place. But whereas the intensity tells about the how the earthquake was felt in a particular area. So that means if you are in an epicenter region, you feel more the ground shaking. If you move away from the epicenter or from the source region or the fault rupture area, then the intensity will keep on decreasing. So that is also depend upon the source, the site characteristics, like that. Professor Surya has told that it is alluvium soil kind of thing. There is a soil amplification will be there in the hard rock type, in the hard material, hard soil is there. then the intensity will be less. So it depends upon the local geological conditions also. But the magnitude of say 6 earthquake, approximate fault length is 6 kilometers, and the intensity, the epicentral area we can have the intensity is 5 and this thing, and maximum it is epicentral distance where the MMI 5 is expected is 40 kilometers. S wave arrival time. So I told you this is S wave arrival time, which gives the maximum ground motion. That will takes place at about. We know that the S wave travels with velocity 3.5 kilometers per second, and so for arriving it may take the 40 seconds like that. That also depends upon the focal depth of the earthquake. So approximate end of peak shaking, that is the general, this is the 20 seconds. That's for magnitude 7 earthquakes, it is the peak shaking is about 60 seconds. Then the duration of the shaking is about the 60 seconds. So like that. So this is give you the complete idea. This is a general idea of how the rupture of the rupture based upon the magnitude of the earthquake, and epicentral distances, and the intensity pattern, and how much time will be taken for the S waves to reach this thing, and what is the duration of the ground shaking. So here earthquake early warning system. There are two types of earthquake early warning systems here. One is the on-site earthquake early warning system, and another is the regional earthquake early warning system. So on-site earthquake early warning system is basically a strong motion oscillograph. It may work upon the this is the ST-LT ratio, and maybe on the threshold level of the ground motion, or maybe acceleration spectra kind of thing. But when it determines the this expected ground motion based upon the first P arrival time from a single station. So it is a very is a local sensor, and warning time is less, because if you are close to the if you are away from the epicentral distance, you have some warning time. If you are close to the source region, then the warning time is very less. So it depends upon the S minus P is arrival time of S waves and arrival time of the S wave. That is a difference. It depends upon this thing, and it is a very low cost sensor. It is just a strong motion sensor. It is inbuilt processing model. As soon as the acceleration of the ground shaking reaches to a certain extent, it gives some kind of alarm kind of thing, and it is less reliable, because if any traffic goes, if due to the vehicular traffic or any spurious kind of blasting or anything, so they get triggered. And the warning may be false warnings. And another thing is that now the approach is that wherever in other parts of the world, in everywhere, it is the regional earthquake early warning systems. So regional earthquake, we know that these are the areas. For example, in USGS, then the West Coast. This is the West Coast has the potential for the future earthquakes, and so we know the areas where there is going to be potential earthquakes in the future. For example, for us, Himalayan region. So we know that there is the central seismic gap. So for last 200 years, there is no earthquake. So no earthquake. So this is we know that this is the central gap is there. In central gap, there is a Congra earthquake in 1805, and after 1934 Nepal earthquake, there is no. So there is there is no major earthquake of magnitude 8 and above in that area, and it is a potential zone for the future activity, and which is just 250 kilometers from the Delhi cap. So we know that these are the areas, maybe the potential zones for the future earthquakes based upon the strain accumulation calculated from the GPS studies. So this is the regional earthquake early warning systems will target to the particular area only. For example, if you target for the say in Kumaon region, and then you cannot do for the earthquake early warning for the earthquakes occurred in the northeast part of the country, in the Himalayan zone of the northeast part of the country, because the sensors are to be located close to the source. The accelerometers, whatever it may be the short period sensors or the accelerometers, or or should be located close to this source. Here the sensors also, there are two types of sensors, because the in ground motion, for example, if you are close to the source, then the ground motion is the order of the, so you feel the intense ground motion maybe the order of few centimeters or meters per second when you are when the epicentral region. So when you away from the epicentral region, the ground motion is maybe in the millimeters per second or micrometers per second. That is not felt by the humans. This thing. So this instrumentation is also divided into the two categories, which measures the strong motion, which measures the weak motion. Weak motion we call it as the seismometers, and the strong the equipments which measure the strong ground motion, we call it as accelerometers. So basically, the accelerometers measure the ground acceleration, and the seismometers measures the ground velocity. So these are the weak motion sensors. So when sensors generally, because we are going very close to the source, so we have to opt for the to measure the strong ground motion. So we go for these accelerometers, and this is the, since we are located at the close to the source, the sensors are located at the close to the source, so we will get the warning time will be more. So because we are detecting the this ground motion at earlier stage, and we have a lot of lead time to inform to the target cities like Delhi, Dehradun, and this thing. So we have sufficient time, say some order of few minutes to few seconds, to inform to the public and the disaster management authorities. So travel time. So this S-wave travel time, and this is a more complex, because the earthquake, you cannot expect that earthquake will happen in that source region only. It may be happen different times, and also the a lot of complexity is involved to develop the algorithms for the regional earthquake warning system. We will discuss one by one how the other countries are doing, and even this IIT Roorkee, what the methodology they have adopted. So they are more reliable, because it is not from the one sensor, it is a group of sensors are involved in giving the warning. So this is the regional earthquake warnings. So from the initial part of the view, we determine the source parameters, and then issuing earthquake alarms to each stations. And the on-site, it work only on the based upon the one on-site one instrument only, and it may be and it estimate the ground shaking from the what is the impending ground motion. So this is the lead time we will get it from the on-site early warning system and the regional earthquake early warning system. So for example, in the case of the warning time, what is the lead time we will get it. In the case of if the epicentral distance is about 200 kilometers, in the case of regional earthquake early warning, we will get the lead time of only 50 seconds. In the on-site early warning, we will get about 20 between 20 and 25, let's say 25 seconds we will get the lead time. So let us say, because we detect the P waves, and the P waves we have to estimate the size and rupture size of the earthquake, the potential the damaging portion of the earthquake. That may take some processing is also required. Let us say if you take the 3 seconds processing time for the on-site and 10 seconds for processing time for the network, and these are the lead times, general lead times we'll get it for the earthquake early warning system. So basic earthquake early warning system and models. This is the first, we should have the dense accelerometers. We have the sensors which can detect the ground motion. So as soon as the earthquake happens, and then automated decision making framework, because this is because we cannot use the satellite communication here. See, the satellite communication will take because the packets, the data will get transmitted to the satellite, from the satellite to the VSAT hub, the hub at the hub, from hub to again it will go to the satellite, and again satellite it will come back to the receiving station. So this is so roughly it will take the about 800 milliseconds to 1200 milliseconds. Say 1 second approximately, that latency will be, the travel time will be there in the case of the VSAT communication system. So we have to go for the point-to-point communication system like GPRS communication or wide-to-wide transfer communication system to have the foolproof communication. This is a very, very important part of the earthquake early warning system. We have to have very robust telecommunication system, communication network from these accelerometers to the receiving station, and computer algorithms, because this is always, it is an evolving process. So we have to come out with the ground motion prediction equation. Once you because we know that there are the soft sites are there, there are hot sites are there. In soft sites we'll get the ground motions are very high, the peak ground accelerations are very high. In the case of the hot site, the PGS and the ground shaking is somewhat lesser. So depending upon the area, and for each area we should have the ground motion prediction equation. Once we know that this is an earthquake has happened and so much it has the potential, this is the estimated magnitude from the initial magnitude, and then we should be able to tell that at different locations this is the expected ground motion at different areas, so and take the necessary actions. So this is all here. There is, in earthquake early warning system, there is no personal involvement. Everything is machine to machine communication. So once you develop the algorithm, everything is automated system. It is not like that in our earthquake monitoring center, the earthquake comes, some duty officer will analyze the waveforms and disseminate the information to the so that is all something it is not somewhat manual intervention is there. In this case, earthquake early warning system, because the lead times we have to very small, in the order of few seconds to 1 or 2 minutes only. So that means everything is machine to machine communication only. So the sensor network detects, and then computer algorithm process the location, magnitude and fault rupture, and then ground motion prediction equations tells about what is the expected ground motion at each site, and then information is disseminated to all the decision to the authorities involved in the rescue operations. So the dissemination channels. So the dissemination channels is that, so we have to pass the, for example, have to pass the right kind of information to the, so to the each for a hospital, the information to be passed is different. For the nuclear plant, the information to be passed is different. For the hydroelectric stations, so we have to make the whatever the information we derive from the earthquake early warning system according to the need of the user, and it has to be tuned and it has to be disseminated in a mass way to the all the concerned personals. So end users, for example, here end users, because the lead times are very small, here it is a order of it is a life-saving. We have to take the actions. So the once we receive the alert, the recipients, the nodal officer, the emergency manager should be in a specific. So they should know what actions to be taken, what immediately after receipt of the alerts. So this is again regional earthquake early warning system. So say again, I am repeating the same thing. So P waves travel with 6 kilometers and S wave 3.5 kilometers second, but the alert will go at. So this because the CP waves has the very low velocities in comparison to the electromagnetic waves. So we can take that information. So once it gets recorded, the information can be passed to the central receiving station with the speed of light. So the earthquake has happened here, and it has been detected by so many sensors, and it has to so the denser and closer the sensors to the source region, the greater the so we have the more the lead time and more the accuracies for the warnings. So multiple P of the, so this is the event initiation, single wave P wave observation, multiple P wave observation, data sent to the data center, verification of event data, and then common alert protocol alerts are sent to the all the stakeholders. So, so for example, so if you are in the, for example, if the earthquake happens within the city, say for example 20 kilometer, 25 kilometer, so then there is no because the S waves which travels with the 3.5 kilometers per second, and you require the processing time of the 10 seconds. So because once you get the P waves, you need at least 10 seconds of time to tell the this is the strong ground motion is going to come. So so the 10 seconds means the yes, by that time S wave will reach 35 kilometers. So that is a blind zone. So in that blind zone you cannot issue any warning at all. So if the earthquake happens very close to the your area, and those sensors are located, dense network is there, but you cannot inform, you cannot give the warning, and that for that warning will be invalid by the time you issue the warning. So the ground shaking has already been started. So that area we call it as a blind zone. So earthquake early warning is possible only when notification can be sent through the communication system ahead of the seismic waves. So so we have to before the strong ground motion comes, before the S waves or surface waves comes to the region, so we have to receive the communication notifications, then only it would be useful. So if you strong ground motion is there, as already you are experiencing and the alert has come, then there is no use at all. So that area we call it as a blind zone. So shaking can take some seconds to minutes to travel from where the earthquake occurred to the alert area. So it generally, the more the distance from the epicenter region, the greater possible amount of warning time, but that is not always true. So but it generally happens, happens. So the greater the possible amount of warning times, if the distance is more from the epicenter region, we have the more warning time. So to maximize the warning time, the system must minimize the delays in data processing, communication, and delivery of earthquake early warning. So the system is be always in working condition, because the earthquakes happens once in a blue moon. It is not a everyday phenomena like weather. So it should be very reliably they are working, and in harsh weather condition, Himalayan the topography is very tough, very complex topography, and there is no electricity also in most of the areas. If you go interior to the Himalayas and this thing, so everything has to come from the solar power, and it has to work reliably, and reliably has to transfer the data to the warning centers for earthquake early warning, for issue of earthquake early warning. So what is the blind zone? So blind zone, area around the epicenter where no warning is delivered before the arrival of strong shaking. So because, for example, for example, if you take the this focal depth is 8 kilometers, and processing time is 5 seconds. So means for example, because the waves come from the this hypocenter region to the surface of the earth, and then the shaking will start. So that means, so if the processing time this much and the hypocentral depth is this much, and we have the epicentral this blind zone about 20 kilometers. For example, same thing. For example, focal depth is hypocentral depth is focal depth is 8 kilometers of the earthquake for the same earthquake, and processing time is 11 seconds. And then so that means the blind zone is 42 kilometer radius. So from the around the epicenter. So that means, so you have the minimum reliable processing time to inform to reduce the blind zones. And also here, so there is a graph is there. This is a you have to detect the earthquake. So for the detection of the earthquake, you have to have the sensors. That sensors also to be located close this thing. And also for reliable estimation of the parameters of the earthquake, more data is required. More data is required means more sensors are required. So more sensors means the interstation spacing between the sensors should be as small as possible. But it is so there is a graph here. You can see that interstation distance from starting from 1 to 3, 10, 20 this thing. So if the interstation distance is about 20 this thing, the blind zone radius is about 25 kilometers. So for example, focal depth is 50 kilometers. The blind zone is the blind zone. So the blind zone is start from the 50 kilometers. Even for the interstation distance 50 kilometers is that the blind zone is 10. So that means what we are learning is that if the earthquakes, if the focal depth is more, the blind zone is decreasing. If the shallow focus is there, then the blind zone is increasing. This is inversely proportional. So means the more the focal depth, more if the earthquake is more below to the surface, and it is below to the surface, maybe 30, more than 33, 34 kilometers, then the blind zone is very less, and the focal depth is very shallow, let us say 10 kilometers, 15 kilometers, then the blind zone is very small. So this is inversely proportional. So here you can see the graph. Here it is the warning time. This one will represent the warning time, and this one is the this is the arrival of the S waves. It takes more time, and the arrival of the P wave is taken as the this blue color, and this is the warning time. For example, it is the so for 100 kilometers this thing. So this is the so 100 kilometers. The warning time would be approximately so say 22 seconds, like that. So that is lead time. We'll get it. So the interstation distance, interstation. So we have to have a very large density of network network in the source zone. So we do not know the even where. So initial part only I told that there is no we do not know where the earthquake happens, and we are making some assumptions, and this is the potential zone for the future earthquakes, and we are installing the sensors. So but the earthquake happens away from the our what we from the away from the network and this thing, then the problems will start, and our maybe warnings may go wrong, and it may lead to the false warnings also. So but everything is, it is a very tricky situation when that's why we should have a very dense network all along the source region. What we think of, say 200 300 kilometers area, we should have a very dense network. So variation of warning, for example, locations means site is at 16 kilometers, 25 kilometers, 50, 75, 100 kilometers from the earthquake epicenter as a function of the interstation distance. So here the interstation distance is the distance between the one observatory to the another, average distance between the two observatories. So if you have the dense network, and dense network is also like that, it is a compromise. So for example, it is the interstation distance is there. So for example, if interstation distance up to 10 kilometers, it is not making much much useful for the warning time. So for example, if you have the interstation distance say 5 kilometers also, it may not lead to the warning time. Warning time means it is a lead time, how much time we'll get for the early warning this thing. So at least you see here, so the interstation spacing from the here this thing it has about 20 to 25 kilometers. This is 10, 20, 30, 40, like that. So between the 20 and 25 seems to be very advisable for the establishing the this earthquake early warning system.
Hello, sir. Sorry to disturb you, sir. Just
Yes,
a gentle reminder about the time constraint, because of the time constraints.
How much time I have now? Oh, yes.
Sir, you can take 5 to 10 minutes more.
Okay, I will rush through. So these are the regional earthquake early warning systems around the world, and in the recently this IIT Roorkee for the Uttarakhand earthquake early warning system has been started in the last month in August 4th. So there are different countries, and last year also in 2019 October, this United States also started the earthquake early warning system called the Shake Alert. So interdependence of the magnitude and distance of the PCA threshold. For example, it is PCA is a very important factor for which is important factor which tells about the intense of the ground shaking. For example, we can see that what is the PCA with respect to the epicentral distance has been plotted. So for example, this is the 2% G. 2% G means approximately 20 centimeters. 20 centimeters per second square. So that means this is the where the human will start the shaking. It is in MMI scale. It is a 4. It is there. So felt by many, frightened by. So it is frightened, and people will move away from the indoors, and there is a plaster will fall, and so that kind of damage will start from the intensity 4 onwards. So intensity of 4, for example, magnitude. For example, it is there 4 magnitude earthquake is there. It will be there up to 6 or 8 kilometers. We can find the 2% G. So it is the graph which tells about the epicentral distance with respect to the as a function of the magnitude for PGA. So, so for example, we go to the how the recently this is in 2019 October, this USGS has commissioned the shake alert system, one of the best so far in the world, and they have the so much they targeted for the west coast of the California, Los Angeles, and so they have the so they have about 1,675 sensors all along the west coast with the station spacing in urban areas 10 kilometers, in the source areas 20 kilometers, and low risk areas 40 kilometers. You can see the station spacing. The spacing is very small, and the data is through RF communication transferred to the, and it is all solar panels, and so data get transmitted to the nodal centers and then to the processing center. So shake alert uses the, because once you receive the data, it has to be authenticated whether it goes for the strong ground shaking. So they use the different algorithms. One is the earthquake point source integrated code. This is the point source model which calculates the normal what we do in the earthquake monitoring. That is the source of what is the epicenter of the epicenter focal depth and magnitude, and then fine fault detector. It will get initiated for the magnitude when it is EPIC tells that the magnitude is going to be more than 6. It will find out the rupture length, what is the earthquake rupture, how it is progressing, how the rupture is progressing. And geodetic algorithms, they also take the GPS data also, and GPS data will tell about the actual ground motion amplitude, and it tells use the right approach for the magnitude estimation for the larger earthquakes. And the plum model is a plum model. It is being used in the Japanese JMA earthquake early warning system. So it is a local undamped motion algorithm. So here it is it doesn't measure any ground shaking or anything. It is just the intensity will be measured. Intensity, how the intensity is increasing from one end to another. So based upon the intensity, how the intensity is progressively increasing, and based upon that gives the how the propagation of the fault is how the rupture is taking place. So all this will be calculated independently, and will go to the solution aggregator, and then the ground motion. Then it will go to the site-wise prediction equations for the at different areas, and then it will be disseminated to the all the through, and it will prepare the maps and how the rupture is going to happen, what are the expected PGA value, whether you have to what actions to be taken, everything it will go to the users for a different type of users. So in the earthquake early warning system of the US is a very advanced one, and they do not have only one center. They have the centers at 4. The data will go simultaneously at Seattle, Pasadena, Menlo Park, and Berkeley, and the same thing is processed, and then information will be disseminated as a single one by their group. So this is already so the project was another thing is that the Indian Institute of Technology Roorkee has launched the just now in the last month they have launched the Uttarakhand State Disaster with the help of the Uttarakhand State Disaster Management. There are about 184 stations, 100 sirens, and I will come here. And I will come to the later part. This is Japanese earthquake early warning system. This is also one of the most advanced one. It started from this year 2003 onwards. They have about 7,000 plus seismic intensity meters, and it measures the what it is soon after the, so their processing time, even if you take the processing time as the when earthquake happens, processing, let us say processing time is 3 seconds or 4 seconds. So within 12 seconds they are going to issue the complete early warning to the all the public and the places this thing the core. But since they have the high density of network, they are considering only the 640 stations with 30 kilometer spacing, and point source model is they uses 270 stations for estimating the source duration and all other things. So Mexican also, the Mexican they have the strong motion network. They have the strong motion network. In the strong motion network, they estimate the amplitude of the average acceleration and instantly how the growth of the acceleration is taking place, and then they will issue the warning. So I can show one some film is there how it is going to the how they issue the earthquake early warning system. Are you able to see the film, please? Hello? All right.
Yes, sir.
Yes, but animation is not coming. Animation is not coming.
Sir, we are not able to see your animation. Sir, if you want to,
Okay, I will show
sir.
it. Okay.
Yes, sir. It won't work like that, sir.
Yes, I think I don't know something problem. It is.
Yes, sir. Yes, sir.
So this is the Mexican, and it is the another one is the this Taiwan using the P alert system. Within 3 seconds they have the accelerometers, and here the source region is located within the Taiwan itself, in the middle of the Taiwan, and they have the very dense network, and all the accelerometers they work on they get the data from the real time, and the earthquake, this earthworm software will process that data, and then shake map will be prepared, and then same in the same way Uttarakhand this Bhukamp alert app is also they released it, and it can be downloaded from the Play Store and Play Store. So this is their this thing, and they have the about 71 stations in the Garhwal region, and P alert stations. What Taiwan has same thing, and Kumaon 85 stations, and the data will go to the IIT Roorkee, and then they issue the warning. And they say that distance. This is the thing. So what is the thing? What is the use of the earthquake early warning system? So once as a user, this is the layman user, we have to go into the drop cover and hold on. So means duck under the table and take cover under the table and hold on till the ground shaking stops. So this is for the schools and other things, layman and this thing. So but there is no point in going outside of the building, because the plaster or something may fall down on our head, and so it may cause damage. So for one thing is that situational awareness. For example, the operational centers. So because before the fire hazard starts, or before the communication failure happens due to the major earthquake, so the operations this monitoring center, the police and other things, they should know about an earthquake has happened in that area, and the strong ground motion is going to come, and we have to initiate the actions. This thing they should know this is what are the areas going to happen before the communication or fire hazard becomes extensive. And this is automated control, because stopping the metro trains, and then say this mm, uh, uh, nuclear power plants and all those things, hydroelectric stations and all those things. So the narrower earthquake early warning system comprises only the technical equipment. It is not like that earthquake early warning system is only a technical view, means get the data and then do the early warning. But it is mostly upon the disaster management issue, because we have to make the society to understand the so once you receive the this earthquake early warning, you know how it has to be communicated to all the stakeholders, how it should be used, because the lead time is very small. So we have to take preventive measures in a very within a very short span of time, and they have to be very good. Once they receive the this thing warning, they should aware of the what actions to be taken. They should fully aware of the actions to be taken. So so it is a wider understanding of the early warning system is required in disaster recovery management. So early warning system key elements. One is the lead time, and the next is the processing, warning, and the system, and flows and interactions, means how the information is disseminated. So these are the key elements. One is the risk knowledge, and all the hazards. We should know the areas which are the having the very risk. For example, nuclear plants, and then hospitals. schools and those areas, risk areas we should know, and then hazard. So another is the monitoring and warning center. So this has to be worked on 24/7 basis, and all the right parameters has to be monitored, and is to be away from this false warning and then missed warning and everything. It should be a proper communication system, and once you receive the warning, what are actions to be taken, what is the response to be taken. So all those things. What are the challenges for the Indian context? We should have the very network in the Himalayan region, close to the earthquake source region, including robust and rapid processing capabilities, reliable, sustainable, and dedicated infrastructure for telecommunication link in hilly terrain. That is a very, very challenging job. Because the approach is also having high altitude and poor approachability, which is prone to landslide and snowfall, etc. So careful assessment of false alarm, missed alarms, and other shortcomings. Timely alerting or non-alerting both have implications, because we have false alarms more, then we lose the credibility of the system. So it should be faithful and it should work reliably, and public education and campaign is a very, very important thing for the end users. So these are some of the things. Here I will conclude my presentation. So it is open for the discussion, and I will invite any queries or.
Thank you. Yes, sir. Yes, sir. Thank you. Thank you very much, sir, for such a wonderful, wonderful presentation, sir, and giving us right from the basics how an earthquake occurs to how the various type of earthquake early warning systems. So, sir, there are several questions, sir, that has been raised. Sir, I will